So our final project was on classification models used for financial fraud prediction. So in 2022, $8.8 billion were lost to fraud, and almost 10% of people experienced credit card fraud in 2022. And credit card fraud was the most common form of identity theft in 2022. Therefore, our goal is to create an accurate credit transaction fraud detection system that has the potential to save billions of dollars a year. And our objective was to develop a machine learning model that will be able to detect fraudulent transactions. The dataset we used was from Kaggle.com, and features included things like time, types of transactions, amounts, origin and destination bank accounts, and whether the transaction was flagged as fraud by the bank's internal system. Now on to exploratory data analysis. So first we have the distribution of transaction types. So here we can see that 99.9% of transactions were not fraud and only 0.1% were actually fraud. And the key takeaway is that obviously our data will now require balancing just because there's so much not fraud over fraud. And for transaction type distributions, we can see that fraudulent transactions only occur for things like cash out and transfer payments rather than things like cash in. And now here we have a graph of the distribution of fraud across the time of day. And you can see that it's pretty evenly distributed across the time of day. So this is probably not a very significant factor in our prediction models. And now for distributions of transactions across ranges, the main takeaway here is that the transactions that are between $0 and around $400,000 accounted for most of the fraudulent data within our data set.
So now I'll talk about modeling. So our goal is to save as much money as possible without necessarily flagging real transactions. So this meant catching large fraudulent transactions while maintaining user experience. And so we decided to prioritize catching larger transactions at the expense of letting these smaller, less significant frauds through. So our emphasis was not on catching the total number of frauds, but rather the total amount of transactions associated with the frauds. So our first model was logistic regression on unbalanced data. So by unbalanced, I mean 99.9% of not fraud data and 0.1% of fraud data. And our expectation was that it would not predict very well because this would have very high false positive rates and high false negative rates. And so it was very biased towards predicting non-fraudulent data. And this is actually expected because the unbalanced data contains much more than non-fraudulent entries. I mean, it contains over 99% of non-fraudulent entries, and this clearly indicates that we need to balance the data. So in order for the model to register the fraudulent data, we need some kind of way to create a balance between the non-fraudulent and fraudulent data. And so what we used was oversampling and undersampling to balance the data. So we undersampled the not-fraud data and oversampled the fraudulent data. And in order to prioritize larger transactions, this was important because banks usually want to catch larger transactions over smaller fraudulent data. And so our solution was custom weighting. So how we do that is we weight each transaction based on its amount and then feed in those weights to the following models I will talk about later. So it essentially gives more emphasis to rows of data that have larger transaction amounts, and the model learns to correctly predict data types with larger transactions. And the second model that we use is logistic regression on balanced data. And so this is a simple model itself, but our goal was to use balanced data and then hopefully reduce false negatives and increase the F1 score. And we tuned the penalty as a hyperparameter, which is a regularization technique. And the performance was much better. So the rate of dollars correctly blocked was 98%, correctly passed is 97%, and the F1 score is 0.4, which is higher than the last model, which is almost 0.
So yeah, I just want to reiterate that we undersampled and oversampled, but our actual data came from the oversampled data mostly. We decided not to undersample completely because that would leave with too few rows to actually do any machine learning on. So we went completely with oversampling. And so the model that we used after logistic regression to try and improve on that was XGBoost, which is basically stands for extreme gradient boosting. So it's an extreme gradient boosting machine. It's at high speed and good for solving complex predictive modeling problems. We tuned the hyperparameters, including number of estimators, max depth, learning and learning rate. Overall, the performance was not as good as we hoped. The rate of dollars correctly blocked was 0.98, but the rate of dollars correctly let pass was actually 0.86, which is not something which is lower than what we would expect for a model like this. But this could be due to user error, as we're not completely familiar with the parameters on XGBoost, and actually because it's not something that we learned in class, but we wanted to go beyond and figure it out for ourselves. Our F1 score is also pretty low, but we hope that eventually we'll be able to figure out the parameters and increase that score. And so the next model that we used is random forest. So it's an ensemble learning method that operates by constructing decision trees and outputting the mode of the class's prediction. So basically, it'll take a bunch of different decision trees and then run them on the sample of data, or sample the data using those decision trees, and it'll sample with replacement. And then based on the prediction of each of those decision trees, the actual class of the entry will be predicted by pooling those decision trees and having them take basically a vote on the actual class of the row. Overall, the random forest had the best performance. The rate of dollars correctly blocked was actually 0.96, and the rate of dollars correctly let pass was 0.99, and the F1 score, which again is the kind of basically a high F1 score, means that you're not miscalculating like false positives and false negatives, and you're not like misclassifying certain things in that respect. And that's basically what we want, because we don't want users to get pinged for real transactions, and we also want fraudulent transactions to get caught. And you can see that this model actually does that, because the rate of dollars correctly blocked was 0.96, which is really high. And also the rate of dollars correctly let pass is also very high at 0.99, meaning that we're actually able to correctly block money while also letting certain transaction pass. And we can see that the rate of dollars correctly blocked is a little bit lower than the ones let pass, because we don't want to completely inundate our users with notifications saying that their real transactions are fraud. So that's basically how we went about it. Some of the challenges and limitations that we had in our data set was that we were weighting larger, or we had challenges balancing the data set, as we talked about, also weighting larger transactional values. We had to figure out how to do that with like an alpha value that we defined as like 2.5. Basically, we kind of squared the data, that each weight, we squared each amount to make it weigh more in our weights array, basically. Hyperparameter tuning also took a long time, which is why it was kind of frustrating at some points, and why we couldn't get XGBoost like super great. Also, balancing between performance measures versus each row versus performance measures for each row versus performance measures for overall money was pretty difficult, because a lot of things weren't able to classify correctly. Also, so for future work, we plan on using PyTorch to speed it up using the GPU, and also to try different methods, and also to try and experiment with XGBoost more and try and make it run better, because it should. But we just need to get used to it. Thank you for watching, and I hope this helps with financial fraud.